Unit 9, Molecular Geometry, pages 234 to 242, Multiple Bonding. Sigma bonds, covalent bonds, result from quantum mechanical effects that are difficult to conceptualize. Nevertheless, chemists use simple models to obtain an approximate understanding of chemical bonding. Consider the ethylene molecule. Earlier in this chapter, we learned that each carbon atom has 3 electron domains, 1, 2, 3. With an sp2 hybridization and 120-degree bond angles. The bonding picture we developed showed that each carbon-hydrogen bond was the result of the overlap between a 1s atomic orbital on the hydrogen and an sp2 hybrid orbital on the carbon. A carbon-carbon bond is formed by the overlap of an sp2 orbital of this carbon and an sp2 orbital of this carbon right here. So if we look at this diagram down here, you can see the overlap of the orbitals. The carbon has 3 sp2 hybridized orbitals, and then 2 of them are overlapping with 2 hydrogen 1s orbitals, and then the carbons have overlapping sp2 orbitals with one another. All of the covalent bonds in the picture above are called sigma bonds. Sigma is symbolized as this, and because the electron density, highest probability, is located along the axis connecting the 2 nuclei in the bond. So this bond is a sigma bond, this is a sigma bond, there's a sigma bond, there's a sigma bond. But we really are only concerned about it here because notice we have the double bond. So one of these 2 is a sigma bond and the other one is going to be called a pi bond. There's a second bond between the 2 carbon atoms in the C2H4. How does this bond come about? Remember that in making the 3 sp2 hybrid orbitals, an electron is promoted from the 2s to the 2p. The hybrid orbitals are formed by mixing together 1 2s and 2 2p atomic orbitals. There is one half-filled atomic 2p orbital that was not used in hybridization. And so here we promoted this electron up to the p orbital, and so we have now only used the sp2s, but we have one left over right here. This electron is going to be involved in the pi bond, while these 3 electrons are each involved in the sigma bond. The leftover atomic 2p orbital on each carbon atom is used to make a covalent bond. Notice how the orbitals overlap in the figure below. Because of the orientation of the 2p orbitals, there is no electron density along the axis connecting the 2 carbon-carbon atoms in the bond. This type of bond is called a pi bond. So if we look at this diagram here, we have the pi bond up above. The pi bond is 0 electron probability along the carbon-carbon axis and maximum probability above and below the carbon-carbon axis. This figure shows all of the bonds in C2H4. There are 4 carbon-hydrogen sigma bonds and 1 carbon-carbon sigma bond. So there's your sigmas between the carbons and the hydrogens. There's the sigma bond between the 2 carbons, and then that second bond is going to be the pi bond between these 2 carbons. Bonding in acetylene. Acetylene, which is C2H2, has 1 carbon-carbon triple bond. So the central carbon atoms each have 2 domains, 1, 2, and use sp hybridization. The sigma bonds are shown in this figure. Notice that each bond has the largest electron density along the axis, connecting the nuclei involved in the bond. This is the hallmark of a sigma bond. The atomic orbitals used in sp hybridization are shown below. There are 2 leftover atomic p orbitals remaining on each carbon atom. So after shifting this electron here, we are only creating bonds with the hydrogen atom and 1 carbon atom, and these are going to make up my sigma bonds between the carbons and the hydrogens. That means that these 2 bonds that remain are going to be used as my pi bonds, or they're going to create the double and then the triple bond. The unused p orbitals are used to make 2 pi bonds. So here's one down here and here's one up here. But the very first bond between the carbon and carbon atom is called the sigma bond, and then we have a sigma here and a sigma here. Determine, example 9.55, determine how many sigma and pi bonds are used in the CH2O molecule. Let's draw the Lewis structure first. So I've drawn the Lewis structure, but I've also drawn out hydrogens, electron configuration or orbital notation, one for each hydrogen. This is oxygen, is 2s2, 2p4. And then this is the hybrid carbon orbitals, 2s1, 2p1, 2, 3. And notice this s electron was shifted over to this hybrid orbital here. So we have this these hybrid orbitals for the carbon. Now, on the oxygen, the 2s2 and this 2p2 right here are going to be my lone pairs. So these are the two electrons involved in these two bonds. One of them is part of the sigma bond with carbon. So we can say this one right here is a sigma bond between the oxygen and the carbon, whereas the other one is involved in a pi bond, and that's going to be right here. This is my pi bond electrons with the oxygen. Here, with the carbon, I could say that this 2s1 electron, now remember, these are hybrid orbitals, and we have an sp2 hybridization. So we're looking at sp2. And so these are the three that are creating the sigma bonds. I've got this one with this hydrogen here, so there's that first sigma bond there. I have this one with this hydrogen here, so there's my second sigma bond right there. And then this one is between the carbon and the oxygen, which we've already marked right there as a sigma bond. This last leftover electron, not involved in the hybrid orbitals, is going to be my pi bond, which is located right here. And so this has a total of 1, 2, 3 sigma bonds, and it has one pi bond. Another way to think about bonding is to consider the mixing of atomic orbitals on different atoms resulting in molecular orbitals. The wave function of atomic orbitals has both negative and positive signs. When atomic orbitals combine, there can be regions of space where the wave function is enhanced and becomes more negative or positive, and regions where the wave function will cancel. Molecular orbitals that have an increase of electron density between the atoms in the bond are called bonding molecular orbitals. Molecular orbitals that have a reduced electron density between the nuclei are called anti-bonding molecular orbitals. So this is a bonding orbital, this is an anti-bonding orbital. Here's your note card, multiple bonds. You're going to have to be able to identify what orbital creates a pi bond. So for example, if you have this sp123 total orbitals in what's normally carbon, if you have only an sp hybridization for carbon, then the other two electrons available must be creating the pi bonds. Hint, the first bond between atoms is the sigma bond. The double and triple bonds will have 1 and 2 pi bonds present respectively. So if you have a single bond, it's a sigma. If you have a double bond, then you have a sigma and 1 pi, and if you have a triple bond, then you have a sigma and 2 pi's.